In the previous slides, we found the determinant of a matrix by using the first row, expanding on the first row. Now, we will see that the determinant can actually be found by using any row or actually any column. And this is going to be called what we call a cofactor expansion. So what is the cofactor? The cofactor is this term C sub ij. So how do we determine what C sub ij is? We take the -1 times the raised to the I plus j. That gives us that plus and minus that system we saw. And so every other term will be plus or minus. And then we multiply by its resulting determinant. So in general, if we choose the ith row, the determinant of A will look of this sort. And if we choose the jth column, the determinant will look of this sort. And so let's actually look at the what we will call a cofactor matrix. So what do we notice happens when I take that term -1 raised to the I plus j? Then if we were to take, say, the A11 space, it would be -1 raised to the 2, which is a positive value, positive 1 in this case. If we were to take the A12, it would be -1 to the 3rd, which will give us a negative. And so we can do this for the entire matrix, and then our cofactor matrix, we notice, will be in the scheme of plus minus, and then we have a minus plus, and goes on and goes on. This is the matrix that we looked at earlier, a 4x4 matrix. And what we did in the past was we found an expansion of this here. Now, knowing that we can use any row or any column using our cofactors, what do you think would be a wise way to choose how to do an expansion to find this determinant? So since we noticed when we did this here, we had 2 zeros, which got rid of 2 sets of values that we had to multiply. But when I look here, I notice that if I do this this column, I actually have 3 zeros, which would leave me with only 1 determinant to find. And so, doing our cofactor expansion, let's look at the only term we'll have here is here, which happens to be the C23. And so, what is C23? We'll get -1 to the 5th times the determinant of the A23. And so what would that be? That would give us what a negative value times the determinant of the resulting matrix here. 1, 0, -1, 3, 3, 2, and 6, -3, 0. And what do we see here? If we were to write our positive, negative, positive, negative, then this would go here, would be negative, positive, negative, positive, and so forth. This would be positive and this would be negative. And so the negative that we got here is indeed correct. So let's find now again the determinant of this matrix. And what will we have? We will have -1 times the determinant that we have written here. Okay, now again we can choose any row or any column. Okay, we have a 0 here and it has 1s here, so that makes life a little bit easier for us. And we'll have a plus, minus, plus again. And so what will we get? The -1 that is on the outside times, we'll have a +1 times when we get rid of this row and this column. 3, 2, negative 3, 0, plus, and in that case, I think that that was originally a negative 1. Yes, it was a negative 1 times the determinant of 3, 3, 6, negative 3. And doing this math, again, we get 33. And so we notice we got here a little quicker than we did the last time by using this cofactor expansion because we were able to eliminate some of our determinants which had a 0 coefficient in front. Now, using this cofactor expansion, notice this is the same matrix we found earlier that we did using an expansion of the first row. Okay. Now, I would like you to think about it again using this cofactor expansion and see if there is an easier row or column. So I would like you to find the determinant of this matrix, which we've actually found. Oopsie, let's do that again. To be 9. And I would like you to choose a row and a column that you feel would be sufficient to use and easier, and see if you get the same determinant of 9. Now let's look at this 4x4. Okay. So we're going to go through it, and it looks like it might be wise to use this first column. And so looking at our cofactors, I know this first term will be plus, minus, but all of these are zeros, so it doesn't matter. And so the determinant of A here would be 3 times the resulting matrix, which is negative 2, 3, negative 7, 0, 1, 5, 0, 0, 2. And now it looks like we need to do here, we can expand on the first row again. In doing so, we'll have 3 times, and then of course here, this is a plus. So we'll have plus a negative 2, which remains a negative 2, times the resulting matrix, 1, 5, 0, 2, which will give us, this is a negative 6 times the 2 here, because this term is 0, and we get a negative 12. So this is the determinant of this matrix, which means that it's not 0, so it is invertible. Let's recall the matrix that we just saw in the last slide. It looks special in the sense that we saw that it was actually a triangular matrix because it has zeros below the diagonal. And a special property we have for triangular matrices, if a matrix A is triangular, then the determinant of this matrix is just the product of the entries along the diagonal. So if I were to find the determinant of A here, it would be 3 times negative 2 times 1 times 2, which indeed happens to be the negative 12 that we got from the previous slide. So if we notice early on that we have a triangular matrix, then we have very little work to do to find the determinant. Now, let's make a note. What happens if a 0 is one of the elements along the diagonal? Then, of course, any number of variables or numbers multiplied by 0 will give us 0. So therefore, that tells us that my matrix is not invertible. Now, I would like you to look at this matrix, the matrices A, M, and B, use cofactor expansion or any rules or theorems that we have seen to find the determinants of these matrices.